Hey everyone, Mr. Fransky here. Today we're going to start Chapter 9, and Chapter 9, I think everyone has heard, is a tough chapter, which is true. It's about what's called infinite series, which is going to rely on some prior knowledge that you probably learned in FST or Algebra 2 or maybe AP Stats, depending on what classes you've taken in the past. It's also going to use some of the calculus techniques that we've learned throughout the course of this year, and it kind of mixes them together just in a unique chapter that I think is really quite beautiful. But it's traditionally challenging for students. So today we're going to learn, just kind of do an intro, and then tomorrow it gets a little bit tougher. Then 9.2, we start to kind of bring the calculus into it, and then 9.3, 9.4, 9.5, as Samuel L. Jackson says in Jurassic Park, hold on to your butts. It gets a little crazy. And it's really cool, but it takes some attention to detail and really persistence to be able to struggle through and figure out what's going on. So the key to this is just to keep up with your homework. Do your homework, and especially if you have questions, please come in and ask as soon as you're not understanding something, or ask a classmate, somehow get the help that you need. Don't let it kind of fester and hold off, because if it builds up, it gets really hard. So be sure that you're taking care of business. All right. So let's jump into 9.1a, which is just an intro to series. So it's kind of a review of stuff that you've probably seen before. And we're going to talk about a special type of series called the geometric series. So let's jump in. I hope you'll be patient with me. My computer's being a little slow today, so if there's some jumping with slides and whatnot, hopefully we're able to overcome it here. So first, let's talk about the difference between sequences and series. A sequence, we talked about that actually in Chapter 8, and then a series is what we're going to talk about kind of all of Chapter 9. So a sequence is just a list of numbers. This is a list of numbers. And sometimes there's a rule to it, but like, for example, you might have the sequence 1, 2, 3, 4, 5, etc., right? This is just the natural numbers, right? So it's just the natural numbers increasing in order. That's just the list of the numbers. That's the sequence. A series, what a series is a sum of the terms in the sequence. So it's the sum of the terms in a sequence. So what does that look like? It looks like, so for this sequence that we have here, it would be 1 plus 2 plus 3 plus 4 plus 5. And you add all of the terms of the sequence. So if you have a finite series, it would stop, right? What we are going to focus on, because Chapter 9 is called infinite series, we're going to focus on what happens as you add this off to infinity. Now, some of you may be looking at this and saying, well, that's dumb. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15. You keep adding those forever. Those are going to add up to infinity, right? So this would be a series that does not converge. Okay, so it does not converge. And we're going to talk about a lot of ways to figure out if series converge or diverge. It's basically what this is all about. So what does it mean? What does it mean for something like this to converge, right? So how is it possible for a series to converge? Well, if we look at that idea of a series, so a sequence again is just going to be a set of terms, right? A1, A2, A3, A4, etc. So there could be some pattern here. It's just a set of numbers, but they're an ordered list, right? We learned that in 8.1 last chapter. So, and a series, I'm going to put this on the last slide, I suppose, but series is just going to be A1 plus A2 plus A3. And there's some notation that you've seen with this before, probably in other classes, to add things up. It's a big sigma like this. So you might have a sigma from like k equals 1 to infinity of a sub k. Something like that, right? This means that you do A1 plus A2 plus A3 all the way to infinity. So you're adding up an infinite number of terms. So how is it possible for something like this to converge? Well, we have what are called partial sums. And the partial sums themselves, we call them SK. They make a sequence of their own. So let's see what we would have here. So in this case, what happens is the sums are the sum of the first n terms. So here, like S1 would just be A1. S2 would be A1 plus A2. S3 would be A1 plus A2 plus A3, right? And this continues, right? So you're coming up with these partial sums. So then SK, or sometimes I call it SN, is going to be A1 plus A2 all the way up to AN. Okay, so you add A1 plus A2 plus all the way up, if this catches up to me. My goodness, all the way up to AN. Okay, so we add A1 plus A2 all the way to AN. And this can continue, right? So these make a sequence of their own. Okay, so this is a sequence in and of itself. Okay, let's see if it'll, not writing catch up. There we go. So this is a sequence, right? You have S1, S2, S3, Sn, right? And it keeps going. And so if this sequence converges, right? We've talked about sequences converging before, right? In chapter 8, we talked quite a bit about that. But if the sequence of partial sums, this is really weird, I'm writing without seeing what I'm writing. If the sequence of partial sums converges, come on, converges, then the series converges. Let my writing catch up here. Oh, and see, I was worried that was going to happen. Jump way ahead. Oh, come on. Back, 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 back. You're getting a preview of what's to come. So if the sequence of partial sums, and get sums in there, converges, then the series itself also converges. Okay, so what that means is if these numbers are converging to some number, then we're good. So for like the last example that we saw, we had 1 plus 2 plus 3 plus 4, etc., etc. Come on. There we go. So the partial sums here, S1 would be 1. S2 would be 1 plus 2, that's 3. S3 would be 1 plus 2 plus 3, that's 6. And as you can see, so we'll go to S4 here. S4 would be 10. As you can see, these numbers are increasing, and they're getting, the gaps between them are getting bigger and bigger, right? So this series would diverge. This diverges. Goodness. This is going to be frustrating. Thanks for bearing with me. Trying to think if there's another way I could make this, but I'm kind of pinned down right now, so I got to do it this way. Okay. So this guy diverges because the partial sums are increasing without bounds. So sometimes you're actually going to see some problems where they give you the nth term of the partial sum, right? So they're like the partial sum is given by this term, and you just have to do the limit as n approaches infinity and see what you get, right? So some examples that where we have partial sums here, and we're going to see what's going on, right? So this idea of adding up an infinite number of things, like we've seen this in calculus before, right? It sounds a lot like an integral, and eventually we're going to get to a place where we use integrals to prove whether these things converge or diverge, but that's going to be like more like 9.5. But for now, just this idea that we're adding up an infinite number of things, it's kind of weird to think that it might actually converge to a number. So let's take a look at two examples here and see what happens. Okay, so and also just to say, if this sequence diverges like we have here, then the series also diverges, right? So if the sequence of partial sums converges, then the series converges. If it diverges, I'm worried to write too much here. I'm going to scoot ahead again. But if it diverges, the series diverges. Let that catch up, and then we'll move on. Who knows how well that's going to be written. If it diverges, the series diverges. Come on, you can do it. Oh, there we go. And it jumped ahead on me again. Oh, goodness. Luckily, I'm teaching this in class, too, so this hopefully not too many people are going to watch this and have to deal with it. Too far back. Okay, so let's take a look at two examples with partial sums. So the first one, we're going to look at the series 1 minus 1 plus 1 minus 1 plus 1, etc., etc. So this is an alternating sequence, right? We have 1, negative 1, 1, negative 1. We're adding all the terms together. So let's think about the partial sums. S1, so that's just the first term is 1. S2 would be the first term plus the second term. That's 0. S3 would be 1 minus 1 plus 1. That's 1. S4, 1 minus 1 plus 1 minus 1 is 0. Now look at this. We have a pattern here, right? We're going 1, 0, 1, 0. And if you were to graph that, you have 1, 0, 1, 0, 1, 0, right? And this would go on forever. Okay, so not super exciting. And we talked about this kind of a sequence before, right? This thing diverges, right? Because it's not converging to 1, it's not converging to 0. This thing diverges. So this series also diverges because the sequence of partial sums diverges. It does not converge to 1 or 0 or any other number, so it diverges. So you may be at this point saying, well, it looks like everything diverges. Well, based on the 2 examples we've done, that's accurate. But let's look at something like this. What if we had 3/10 plus 3/100 plus 3/1000, and we keep added this way, okay? Well, let's see kind of what these partial sums would be. Let's think about these in terms of decimals. So this would be 0.3 plus 0.03 plus 0.003, and keep adding. So we think about the partial sums here. S1, that's just the first term, it's 0.3. S2 would be, let's see, 0.3 plus 0.03, that's 0.33. S3 would be 0.3 plus 0.03 plus 0.003, that'd be 0.333. What's happening here? We're just adding another 3 on the end each time. So it looks like if you went all the way to infinity, the infinite partial sum, looks like it would be 0.3 repeating. That is 1/3. So it looks like this series, if you add up to infinity, is converging. This sum converges to 1/3. Interesting. So this is a special type of series that we're going to talk about today, and it kind of looks like, that is kind of a unique type of series where these are getting smaller and smaller and smaller. These terms are getting really tiny, and by the end, I mean, we're going to be adding 0.000000000, rather there's going to be like a trillion zeros, and then a little 3 at the end. And it's kind of interesting to think, well, the numbers you're adding are getting smaller and smaller. So maybe that's one of the keys here, right? Because over here, these numbers are not getting smaller. In our last example, where we had 1 plus 2 plus 3 plus 4, those also were not getting smaller, right? The only way we're going to have any chance of these converging is if those numbers are getting small. And this is what's going to lead to your first convergence test. So this test is called the nth term test. And what the nth term test says is if the limit as n approaches infinity of a sub n, so if this is the nth term of your sequence, right, is not equal to 0, then the series, the sum from k equals 1 to infinity of a sub k, that sum, so the series, diverges. So it's called a convergence test, and we're going to focus on a whole lot of convergence tests in Chapter 9. But the first one is actually really more of a divergence test, right? So what this says, if you have a1 plus a2 plus blah, 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 if you get off to like some super high numbers, right? If these things are not getting small, so they're not getting closer to 0, that means that what's happening is at the end you're adding terms forever, right? So one example of this would be like if an is like n over n plus 1, right? So then if you're doing the sum of all the terms of the series, the sum of each of the a sub k's, your first term would be 1 over 2, which is 1/2. The next term would be 2 over 3. Next term would be 3 over 4, right? What are these things turning into? As n goes to infinity, what happens to this? There might be some L'Hopital in this chapter, right? So this thing, you can just look at the leading coefficients of this one, right? But 1 over 1, eventually going to be adding like 1 plus 1 plus 1 forever, right? Because as n goes to infinity, these things are turning into 1. So you're going to be adding 1 over and over and over again. There is no way this is going to converge. This thing diverges. So this is the first line of defense. You look at the sequence and you say, well, these terms are getting bigger, or they're converging to some number. It's like, well, at the end, if I add those up forever, that's going to diverge for sure, right? Because if you're adding something over and over an infinite number of times, then that something is not 0, then you're gonna diverge, right? Now, there's an important warning that comes along with this test. If the limit as n, this is very tempting for a lot of calculus students and non-calculus students too. As limit as n approaches infinity of an, if it equals 0, this does not guarantee convergence. And that deserves an exclamation point. Because Sorry, it's kind of tough to write on here when I can't see what I'm writing. So because there are some things where they're getting small, but not fast enough, right? Again, this kind of sounds like integration, right? So an example here, we're going to talk about this a lot. We're not actually going to get to it explicitly until I think 9.4 or 9.5, but 1 over n is a very interesting sequence and series. 1 over n is called the harmonic series. And as n goes to infinity, these are getting small. But the problem is they're not getting small fast enough. If you added up an infinite number of these terms, you actually could get them as big as you wanted. So this would be 1 plus 1/2 plus 1/3 plus 1/4, et cetera, right? So this actually ends up diverging, and we can't prove it quite yet. But for now, I just need you to be able to trust me that this thing actually diverges. So this is kind of proof that if the limit as the terms go to 0, you can't say, well, automatically there you go. If they're going to 0, it must be convergent. That's not guaranteed. All you can guarantee is if the limit is not 0, then for sure it's going to diverge. So in logic terms, this would be the contrapositive of the converse down here, which is a lot of big words if you haven't studied logic. But the converse is not always true, right? If Mr. Fransky answers the door, then he is home, right? That makes sense, right? If Mr. Fransky answers the door, then he's home. But the converse doesn't have to be true. If Mr. Fransky is home, then he opens the door, wouldn't necessarily be true because of the first statement, right? This is kind of like that, all right? Lots of logic. If you haven't studied, it's kind of cool. Okay, so let's take a look at a special kind of series, which is actually one example was the 0.3, 0.03, 0.003 is kind of one of these. So we're going to take a look at here is we're going to look at I think we'll start with 1/2 plus 1/4 plus 1/8 plus 1/16, and you can kind of see the pattern here, right? But what I'm going to say is if you're adding off to infinity here, what's going to happen, right? So we have 1/2 plus 1/4 plus an 8 plus a 16th. You might see the pattern here. The next will be 1 over 32, then 1 over 64, 1 over 128. We're dividing by 2 every time to get the next term of the series. So if we think about our partial sums here, S1 is just going to be 1/2. S2 will be 1/2 plus 1/4. That's 3/4. S3 would be 1/2 plus 1/4 plus 1/8. So that's 3/4 plus an 1/8. 3/4 is 6/8 plus one more is 7/8. S4 would be, it looks like, I think it's going to be 15/16, right? Because we have 7/8, that's 14 plus one more is 15 over 16. So look at this. Look at these partial sums. 1/2, 3/4, 7/8, 15/16. Look like the top number is always one smaller than the bottom one. And so if this goes off to infinity, sometimes you might say S infinity, right? So it looks like, what are these approaching? Well, 1/2 and then 3/4 and 7/8, 15. These are getting close to 1. So I'm going to put a question mark up here and say, is that going to approach 1? If you add these up forever, is it going to actually equal 1? And it turns out that it really does. And let me kind of give you a visual representation of this that I think is kind of cool. So we take a square, and we say the first term is 1/2. Okay? Then the next term is a 1/4. So that would be 1/2 of a 1/2. Right? Next term is an 1/8, so this kind of is a 4th right here, right? So we're adding these together. I'm thinking about this in terms of area, right? So we're taking this area, we're adding this area to it. So far we've covered 3/4. That's kind of our partial sum right now. Then we add an 1/8, which is 1/2 of this. Right? So we've added that now. So now we're at 7/8 altogether that's shaded. And then we add a 16th. And then we would add 1 over 32, which would be this, right? And what's happening is we keep adding a piece of this whole square, right? But we never have to add more than we have like available as space to us that's left, right? So this square is 1 by 1. So if you keep doing this, if you keep dividing by 2, dividing by 2, dividing by 2, do you see how you'll never fill the entire square? And that's very important to this idea of series, is that if you add an infinite number of things, it has to not break out of some kind of number, right? That limit has to approach something. It can't go outside of a bigger and bigger box, then it would be diverging, right? So this is a special kind of sequence, and you may have heard it before. If you keep multiplying by something every time, this is special. It's called geometric. And I think, let's see if my writing will catch up to me here. I'm probably going to jump a slide too. I'm getting used to it now. Okay, this is called a geometric sequence is the terms by themselves, but I'm going to call it geometric series here because we're adding the terms together. Okay, so geometric series is where you're multiplying by something every time, right? So a geometric series looks like this. You have a first term, we usually call it A. Then you multiply by something every time. So it would be AR, and then it would be AR times R again. So it would be AR squared, then AR cubed, then AR to the fourth, and we keep going, right? So this idea that you keep multiplying by something every time, it's important here that we're multiplying by a small number, right? Because we're dividing by 2 every time. 1/2 times a half is a fourth, times a half is an eighth, times a half is a 16th. You could also be multiplying by bigger numbers, right? You could multiply by 2 every time. It could be 1, 2, 4, 8, 16. But if you added those together, right, there's no way it would converge, right? So then it looks like the nth term here. So if we think about n here, if this is 1 and 2 and 3 and 4 and 5. So the nth term, it looks like, is AR, not to the n, right? Because the n, the power here for each one is one smaller than the nth term that we're on. So it looks like AR to the n minus 1, which is going to be important to proving how some of these are going to converge. Okay. All right, so I want to give you a little proof here. The book doesn't do this, but it's very quick, and I think it's worth seeing because it's kind of cool. It's very similar to the sum of the first n digits. But if you think about the nth partial sum of a geometric series, I'm not going to write the geometric series again. We just wrote it on the last page. But the nth partial sum is going to be A plus AR plus AR squared plus dot 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 plus AR to the n minus 1, right? So that's the sum of the first n terms of a geometric series. So what we're going to do now is we're going to multiply all of those by r. So r times the nth partial sum would be, so if I multiply each of these terms by r, and I'm going to slide it over so they kind of line up, right? So the first term would be AR then. The next one would be, so if I multiply this whole thing by r and distribute it, it would be AR squared. The next term would be AR cubed, and we would eventually get to AR to the n minus 1. And the last term, if you multiply that last term by r, it's going to be AR to the n. Okay. Now what we're going to do is we're going to subtract that whole thing from the top line. Okay. So in the front we have Sn minus RSn. And on the right, look at how we can subtract here. So the top line we have an A. These are going to cancel. These are going to cancel. Everything's going to cancel until we get to the last thing. We have nothing, and then we subtract AR to the n. So really what I'm looking for here is I'm looking for a formula that's simple to find the nth partial sum. So what I'm going to do here is I'm going to factor out Sn times 1 minus r equal to A minus AR to the n. Okay, so now I'm going to divide by 1 minus r. So this gives me a formula for the nth partial sum. This is pretty rare. A minus, I'm going to actually factor that a little bit too. Go back here and see if I can erase. I haven't had to erase for a while. Nice. So to factor out an A, I'm going to have A times 1 minus r to the n divided by 1 minus r. And this is a formula for the nth partial sum of a geometric series, which is pretty rare. It's rare that you get an actual formula for the nth partial sum. That's why geometric series are kind of so special, is we can get this actual equation for the nth partial sum. So this means we wanted to add the first 100 terms of our 1/2 plus 1/4. What you would do is you'd say, well, the first term is 1/2, you'd put it there. R is 1/2, so you'd put it here and here, and then the nth power, you put 100 there, and that would tell you what the sum of the first 100 terms is, which is kind of cool. So now what I'm going to do is I'm going to say, well, okay, this is the nth partial sum. So what I want is the limit as n approaches infinity of Sn to equal some number. Okay, so I don't want this to diverge. I want this to end up equaling some number as n goes to infinity. And this is really the question that we're going to focus on for really much of the chapter is, will it converge? And when I first started teaching BC Calculus and I kept having this question, will it converge? I thought about this guy using, I think it's the Magic Bullet blender or maybe the Ninja blender. I don't know. It's something. But he has these videos on YouTube. If you want to go check them out, do yourself a favor. They're kind of fun. And he keeps saying, will it blend? And in this case, he's blending glow sticks. But people send him questions all the time, like, could you blend a cell phone? Or could you blend, like, I don't know, a selfie stick, I think he does once. Could you blend, I don't know, a pair of shoes? And he puts all these things in the blender, and they see if you could blend it up, and it's kind of fun. But so will it converge? Will it blend? Kind of the same thing. So in this case, the question is, will it converge? We had that that nth partial sum, which was A times 1 minus r to the n divided by 1 minus r. So we want n to approach infinity here. Well, where's the only place you see an n here? It's only on that exponent of r there. We know something about raising numbers to really big exponents. There are some numbers that balloon, right? Like if r equals, whoops, too far. If r equals like 5, there's no way this is going to work, right? So if r equals 5, it's not going to work because 5 squared, 5 cubed, 5 to the 4th, 5 to the 5th, it's getting giant, right? What kind of values, when you take them to really big powers, get smaller? Well, how about like 1/2? Right? If r equals 1/2, 1/2 squared is 1/4, cubed is 1/8. That's getting smaller and smaller and smaller. That would work. Which kinds of numbers are going to work for this? And people always say this. They start by saying r has to be less than 1. And I say, okay, well, how about like -7? -7 is less than 1. If you have -7 squared, cubed, 4th, 5th, that's getting bigger and bigger and bigger, right? It's alternating, but it's still getting giant, right? So what's the lower bound? Well, I think if it is between -1 and 1, that's what we really want, right? So if r is between -1 and 1, then we're going to have this kind of special situation where this thing is going to converge, right? This is what it's called conditional convergence. Conditional convergence. Because it converges, convergence, not convergence. It's going to take me out of here. Bear with me. Sorry. I have to get back to my slide here. Go, 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 go. Almost there. Might have gone too far. Thanks for bearing with me. Hopefully you got this on 1.5 speed. Okay, so conditional convergence, not converges. Oh, gosh. They're going to make me right on top of it. That's fine. Go back to my blue. Convergence. Okay, because it only converges when n or when r is a certain value, right? So conditional convergence. And often the way that you see this written, because r has to be between -1 and 1, is they'll write absolute value of r has to be less than 1. This is what's called the radius of convergence. Radius of convergence. And it's called that because convergence. This is so frustrating. I'm sorry. I'm sure it's frustrating for you too. Okay. Let's see if I can actually get to the right slide this time. Come back to me. We're almost done, I promise. I just have a couple examples to show you, and then we're done. Come big. I might just leave it red this time. Okay, this is the radius of convergence because if you think about this on a number line, here's 0, here's -1, here's 1. If you think about that being the radius of a circle, it's centered at 0, right? And the radius is around 0. Oh, goodness. I'm so sorry, guys. They like to move on me. Okay, so a lot of people ask, well, what about if it was equal to 1 or -1? Well, if r was 1, 1 to the n is 1, you would actually have an undefined situation where you'd have 0 on the bottom. So 1 will not work, right? Because 1 to the n doesn't converge to 0. It gets bigger and bigger and bigger. So kind of a generalized idea here is that if you have a geometric series, I'm very wary of writing now because it likes to jump on me. So if you have a geometric series AR squared, etc., then the series, which would be A plus AR squared plus blah, 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 which you could write as the sum from k equals 1 to infinity of A times R to the n, or k minus 1. Often use n for the last term. That's why they kind of like to use k for this. So notice when you plug in 1, you just get a. You plug in 2, you would get AR. Plug in 3, you get AR squared. Okay, this guy converges if and only if the absolute value of r is less than 1. Some people say, well, what if it's negative? That's fine. This will be alternating, but those r values are still, as you get bigger and bigger and bigger, are going to converge to 0. So it's okay to alternate. That's just fine. Okay, so converges if and only if absolute value of r is less than 1. Now here's kind of the cool thing. If you look at this guy, right, as n gets bigger and bigger, what's going to happen to r to the n if it's between -1 and 1? Well, that's going to turn into 0. So we can actually even go beyond and say not only will it converge, we can say what converges to, right? This guy is going to turn into, if that turns into 0, we just have a times 1 on the top. So it's going to be a over 1 minus r. So we can not only say that it's going to converge, but it converges to a over 1 minus r. Okay. So let's check that for our example we saw before. We saw 1/2 plus 1/4 plus 1/8, etc., etc. So let's see here. We just need to know a and r to be able to figure this out. In this case, a is 1/2, and r, I think, is also 1/2, because we multiply by 1/2 every time to get all these numbers. So a is 1/2, r is 1/2. And so we should be able to be, r is 1/2, which is between -1 and 1, right? So we're definitely going to converge, because 1/2 is between -1 and 1. So if we should converge to 1/2 over 1 minus 1/2, which is 1/2. 1 minus 1/2 is also 1/2. So you have 1/2 over 1/2. And that is 1, as we expected. Kind of cool. Ugh. I have 2 examples on one page. Let's see if they'll let me stay here for a little while. Okay, so we converge, this idea that we converge to a over 1 minus r is important. That only works for geometric series, right? So this formula is kind of, we're going to learn throughout the chapter, this is very unique that we have this kind of formula for what a series converges to. So let's do 2 examples, see if they'll let me write them out without jumping out again, and then we'll get out of here. So the first one, we have 2 plus 6/5 plus 18 over 25 plus 54 over 125. We're going to do a dot, dot, dot. Okay, so the question is, does it converge? Okay, does it converge, and if so, what does it converge to? Well, what we're going to look at here is it geometric? So what I always do to check if it's geometric is say, do I multiply by something here that's also multiplied the next time? Well, to get it from 2 to 6/5, I would have to multiply by 3/5. Does that work again? Well, 3/5, let's see, we get 18 over 25. Yeah, so it's 3/5 again. So it looks like we are indeed geometric. Okay, so this is geometric with a equals 2 and r equals 3/5. Doesn't matter what the first term is, right? Because eventually it's going to become smaller, 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 smaller. So see, the first 2 terms are bigger than 1, but then they start getting smaller. They are converging to 0. So it does converge because 3/5 is between, right? Because absolute 3/5 is less than 1. And it converges to a, which is 2 over 1 minus r, 1 minus 3/5. So that's going to be 2 over 2/5, multiplied by the reciprocal there. That's 2 times 5/2, which is 5. So if you look at these partial sums, the nice thing is you don't have to do that anymore, but if you look at these partial sums, they would add to things pretty quickly that are close to 5, right? 6/5 is what? That's 1.2, so we'd be at 3.2 already. Then we're going to be adding more and more and more. We'd pass 4, we get closer and closer and closer to 5 with those partial sums. One more. All right, what if we had pi over 2 plus pi squared over 4 plus pi cubed over 8, etc., etc. Okay. So what's happening here? Well, it's pretty clear every time we're multiplying by pi over 2. So r is pi over 2. Now, some students get into this habit, and a is pi over 2, of looking at something like this and automatically just throwing it into this formula, this a over 1 minus r. But you got to think about it. Pi is like 3.14, right? Divided by 2, that's like 1.5 something, 1.5 and change. That is bigger than 1, so this thing diverges. Those numbers are going to be getting bigger. Even though it's tempting, because we might not automatically think pi over 2, oh, that's bigger than 1, but this thing diverges. All right, thanks for your patience. I think we could have done this in about 20 minutes if all the video issues hadn't happened. So thank you for following along. I love you guys. That's why I'm here. Have a great day.